Hello, welcome to new lecture series on mathematics for class 11. This is based on chapter 1 of NCERT syllabus. So this is lecture 1. I will talk about set theory today. My name is Sangam Banerjee and my details are given below. In the first slide, I will give introduction to what you mean by Venn diagrams, union between two sets, intersection between two sets and difference between two sets. Union is represented by capital U, intersection is represented by inverted U and difference is represented by capital delta. This introduction will help you in understanding the remaining talk very easily. In Venn diagram method, set A, you represent it as a circle and the element of the set you put it here. So these are numerals from 1 to 7. This is set A and numeral from 7 to 10 is in set B. So there are few common elements like 5, 6 and 7. So when you say union of two sets, you only write it once. So here 1, 2, 3, 4, 5, 6, 7. Here also, but I don't write it again because already been included in the set. So in a set, repetition of element is not allowed and 8, 9, 10 only belongs to set B. Actually, this is not a correct way of writing. The correct way of writing is something like this, where you have this set A and this is your set B and the common element, because this 5, 6, 7 belong to A as well as 5, 6, 7 belong to B. So this position is called the intersection area, and so I can write this A union B. Again, I can write same it is because I have just made a union of these two. So again, I write the same element 1 to 10 here, and here again this A union B set, this is the whole thing. So these are the numerals which are in this combined one. So either each element belong to either A, like 3 belongs to A, or 8 belongs to B. So it is A or B, similar to this. But A intersection B, there is a common element is only 5, 6, 7. So this element belongs to both. It belongs to A as well as it belongs to B. So I write A and B. In union, I write A or B. And interesting to note here, which we will see much more in detail in later few slides in this lecture. And here we will introduce a term called number of element in A union B is nothing but, see here, if you see, you have these numbers plus this number. There are how many numbers? 7 numbers are here. And here 1, 2, 3, 4, 5, 6 numbers are there. 7 plus 6 becomes 13. So when you say numbers, then it is different from a set. So here number of elements A union B, this is this number plus this number minus, because you have now counted it twice, so you have to subtract this 5, 6, 7 common ones. Just stop it, pause it wherever you find difficult. You again listen to what I have said. And complement of set A is represented by A prime, that is your 8, 9, 10, which does not belong to A. The element which does not belong to A is written as A prime, and this 8, 9, 10 don't belong to A. So this is a complement of A. So we will deal all this in much detail. This is just a preliminary thing which I am trying to explain so that later on it will be easier to understand. So similarly, if you have a set called C which has an element 1, 2, 3, 4 and set D 8, 9, 10, there is no common element. So union of these two set C union D will be 1, 2, 3, 4 and 8, 9, 10. Okay, others numbers are not there, so you don't have to write here. And there is no common element, that is C intersection D is empty here. So these are called empty set, and you will see the property of this empty set is very important in set theory. Now to take it further, what is the difference between these two sets A and B? So same as this. So you see, these are the element 1, 2, 4 and 3 belong to this shaded region, this blue shaded region. So what does it mean? This A minus B means all the elements in set A minus all the element in set B. Anyway, I am not considering this yellow region. So this 5, 6, 7 belongs to B. So you have to delete this number. So A minus B will be only 1, 2, 3 and 4. So similarly, B minus A will be this set B, and you delete the element which are there in A. So these are common elements. So these 3 only will get deleted from this set B. So B minus A is only 8, 9, 10. All this we will discuss in detail in coming few slides. This is just an introduction, this first slide, so that as I said earlier, it will be easy for you to follow the whole lecture much more quicker and easily. Now, so if A is a set which contains these 3 elements 1, 2 and 3, and set B contains same element but little jumbled, say 3, 1, 2, then actually they are same set, and hence we write set A equal to set B. So it is immaterial how you arrange them in set theory. The only thing which matters are the elements. So you have your 3 elements, here also 3, and they are all same, identical. Here 1, then 3 and 2. So that's why A is equal to B. So similarly, if A is a set which contains say 1, 1, these are the 3 ones, then 1, 2 and 2 3s, then it's same as 1, 2, 3. So in a set, you need not repeat this element. So you can club them because they are all same. As 1, then 1, 2, and since instead of 2 3s, I write 1, 3. So this set and this set is same. But definitely number of elements in this set is different. than the number of elements in this set. We will see all these in more detail in the coming few slides. I would like to introduce here one more point before going to the main topic. That is, if set A contains these two elements 1, 2, then power set of A you represent as P of A. This is a power set of A. What it means that you take all the combination or permutation. There is a difference between permutation and combination, and I will come to this in chapters containing permutation combination. So what I mean is that you take, there are three elements actually. This is 1, 2, and one more set is your empty set. So here for set A containing these two elements, the power set of A one can write as, we will show in next few slides that every empty set is a subset of all set. So I put here one empty set. We will come to this, just have patience. And then this element I take and make it a set. I can take this element and make one more set, and I can take a combination of this comma this. I can make a set of this, but it is not necessary to write 2, 1. So that we will neglect. So we will take only those combination where rearranging this doesn't matter. So we will only count that one as one single set. So number of element in power set of A I write as like this, n capital P of A, or I can write modulus of PA. So there are 4 elements 1, 2, 3 and 4. So I can write this modulus of power set of A is equal to 4, or number of power set of A equal to 4. So let us start with elementary set theory. So what is a set? A set is a well-defined collection of objects. Objects, element and member of a set are synonymous terms. That is, they mean the same. So either you can term it as object or element of sets or member of sets. So there are two methods of representing a set. One is the roster or tabular form. You can represent in a tabular form, or second is a set builder form. So what is this roster form? So I can label set with capital letters, and the elements or object, these are called the elements or objects or members of the set. I include it in this curly bracket and separated by comma here. So these are all numbers which are divisible to 42, and here set B is a set of all vowels, and here set C is a set of all odd numbers. So this is, you have written in a form of a row or a tabular form, and in a set builder form you write a statement. So this tabular form one can write in terms of a set builder form, that is this set A, this is your curly bracket here X, and this symbol I will be using many symbols, and as I proceed in the talk, please be careful to note it down what the symbol means. This symbol is such that, okay, so A equal to X such that X is a natural number which divides 40. Here this is the one. And set B is Y. This Y are the elements such that Y is a vowel in an English alphabet. And here set C, I can write set C are element Z. So there will be many elements. Z is variable such that Z is an odd natural number. So all odd natural number will form this set C. And this is ... means it is an infinite set. These are two finite sets. Again here, if it is suppose here this set D is nothing but it is X such that X is a square of a natural number. So this is 1 square, this is 2 square, this is 3 square, this is 4 square, 5 square. Or I can write X such that X is equal to n square, where n belongs to natural number. And here set E, I again write here 1 by 2. So 2 by 3, comma 3 by 4, then comma 4 by 5. So that is nothing but n by n plus 1. So you have X such that X is equal to n divided by n plus 1, where n is a natural number. Again, this is also an infinite set. So now I introduce another symbol, is called belong to, is an epsilon, a lowercase epsilon. So this means here 2 belongs to A. So this element 2, it belongs to this set A. Okay, so this is how you write. Here you write 2, when you cross it here, does not belong to B. So here 2 is not there, it's only vowels are there. Similarly, 2 does not belong to C. It is 2 is missing here. Similarly, 2 does not belong to D. Okay, and similarly 2 does not belong to E. So these are the symbol. This is belong to and this is does not belong. And in roster form, the order in which elements are listed are immaterial. I can jumble them up, but all elements should be there. So it is immaterial whether I bring this 6 here and 2 bring it there. It is immaterial. All the elements are present in this set. You think it as a container. Okay, so whether you jumble it, this set A contains all these elements. It is interesting to note here that all infinite sets cannot be described in the roster form. Obviously, if it is an infinite and if it doesn't have a particular pattern, I cannot, this is a pattern, X is equal to n square is one pattern. So if I cannot represent in this certain kind of a pattern, then I cannot write set in a roster form. Okay, so here what I have written is all finite set cannot be described in a roster form. For example, a set of real number cannot be described in this form. So it will have many real numbers. Okay, between two real numbers there are many real numbers. So that means it is an infinite set. So because the element of this set do not follow any particular pattern, you cannot represent this in a roster roster form. But you can write it in a set builder form where you can say set S is equal to X such that X belong to real number R. But you cannot write it in a roster form. Now we define what is an empty set. A set which does not contain any element is called the empty set, or the null set, or the void set. And their size or cardinality, that is number of element, is 0 in an empty set. Now let us see an example for an empty set. So I write this set A is equal to X such that X is a student presently studying in both class 10 and class 11. So this is not possible. So this has no element. So there is no student. So I keep this as an empty set. So this is in this set is empty. And this can be also, this empty set is either represented by these two curly braces, or you use this symbol which is very similar to phi. So I may be calling it phi sometime. So what it means, that common element of two disjoint set, this class 10 and 11 are two disjoint set, okay, and there are no common element, is an empty set. Okay, so common element of two disjoint set is an empty set. Empty set, this is how I represent it as, is a subset of every set. So how do I prove? So let us prove by contradiction. We have studied extensively in class 10 what is proved by contradiction. So let us use that. So here assume that this empty set is not a subset of it. So here what I am saying, my statement is empty set is a subset of every set. So by proof of contradiction, you have to assume that this empty set is not a subset of A. We start with this assumption, that is, this empty set is not a subset of A. So this symbol is for a subset, and if you cross it, it becomes not a subset. So we assume that this empty set is not a subset of A. We start with this. So here it means that there is some element which does not belong to A. But if I say that there is some element, then it is a contradiction, because empty set should not have any element. So here what I have written is, so it implies that there is an element in this empty set which does not belong to A, but empty set should have no element, and hence this is a contradiction. So the empty set must be a subset of A, because it was contradicting our first assumption. That assumption was not a subset. So since it is contradicting, I say therefore this should be a subset of A. The empty set must be a subset of A. So it is interesting to note that the empty set is a subset of all sets which we have shown here, and yet the empty set is disjoint from all set, that is no common element, that is A intersection phi equal to phi. This sign is a symbol of intersection. So here it says that elements in A and elements in this empty set, there is no common element, because this is empty set. So it is an empty set again. This symbol denotes because or since. Now if A intersection B, you have some common element, that is this C belongs to A as well as C belongs to B. So this symbol, as I said, is a symbol for intersection, and so this implies that C is a subset of A and C is a subset of B. So from here it means that phi is a subset of A and phi also is a subset of phi. So here I write phi is a subset of A. Now why this empty set is called a set? Because here I say that any operation on sets should give rise to a set even if the set do not contain any element, and hence empty set is called a set. So as I mentioned earlier, a set which is empty or consists of definite number of elements is called finite. Otherwise the set is called infinite. Example, X such that X belongs to N, and this is a condition, that is X minus 1 into X minus 2 is 0. So this condition is only satisfied for say X equal to 1 or X equal to 2. So this is a finite. So you have only two number, 1 comma 2 is finite, and here X such that X belongs to N and X is prime, and this prime can go to very large number up to infinite. So it is called infinite set. Now two sets A and B are said to be equal if they have exactly the same elements, and we write A equal to B. Otherwise the sets are said to be unequal, and we write A is not equal to B. Now let us recapitulate what we have said in earlier few slides. So these are called Venn diagrams, and this I represent set A as this circle here, and the elements are this shaded blue, and this is set B and its element are again this shaded region. So now if I combine them, that is A union, this I call it, this symbol is called union. So A union B means any element in A or in B. So both these circles are shaded. And then next one is common element, that is element present in A as well as present in B. So this is the intersection. So these are the common elements. So element here is not present here, and element here is not present here. So element common to both set A and B have shaded in blue here, and you call it A intersection B. And since the element belongs to both, to A also, and element here belongs to B also, and you write as A and B. And in this case in union it is A or B. Element can be here or here. So here you see this shaded region belongs to A also and belongs to B also. Next is set A minus B, that is you have set A and you subtract B. So this is shaded region is A minus B, or you can call it A A not B. Okay, this minus B I can call it as not B. And similarly here, this shaded green region is this total B minus A. So this is B not A. So these are very simple and not difficult to picturize it. So let us write in words this one. A set with all elements present is called union and is labeled as capital U here, or one can write A or B. Okay? And this symbol is called a union, or one can think it as an OR, which we have described here. So how do you write in a set builder form? You write A union B is equal to X such that X belongs to A or X belongs to B. So similarly, two sets having common element is called intersection and labeled as this is a inverted U, and you can call AND because it belongs to both set A and set B. And how you write in the form of set builder form, A intersection B is equal to X such that X belongs to A, X belongs to A as well as X belongs to B. In union it was OR, either X belongs to A or X belongs to B. And differences is labeled as minus sign, that is A not B or B not A. So here, as I have mentioned earlier in the Venn diagram, so I write A minus B in a set builder form, X such that X belongs to A, it belongs to A but does not belong to B. Similarly, B minus A is X such that X belongs to B and X do not belong to A. So these are very simple and I am going slowly because these are new concept to you all. Now subset which we had introduced earlier, that is set A is said to be a subset of B if every element of A is also an element of B. Here I have shown here. This is set A and all element in A belongs to this big set B. So one can say that set A is a subset of B. So here are some properties. A is a subset of B if A belongs to A, if some element A belongs to A, then this A belongs to B also. And if A is a subset of B and B is a subset of A, that will happen only if and only if A equal to B. We also point out that every set A is a subset of itself, that is A is a subset of A. And as we have shown earlier that MC set is a subset of every set. Now if A is a subset of B and A is not equal to B, then A is called the proper subset of B and B is called the superset of A. So now let us see it in an example. If set A contains element 2, 3 and set B contains this element 1, 2, 3, 4 and set C contains again same element 2 and 3. So from here I can see that this A equal to C and I can see that all the elements of A belong to B also, this 2, 3. So one can say that this is a superset and this 2, 3 is a subset of this and this set A is also a subset of 2, 3 or vice versa. So one can write symbolically that A is a subset of B and A is a subset of C, and you note here that you have an equal to sign here. That means this all the element of set A is equal to all the element of set C. So I write this. But this is also a subset. This is called the proper subset because this really properly goes into it. And here set A and C exactly matches each other. So this symbol, a C-like symbol with underline means is a subset of, and without this underline means is a proper. So if it is like equal to sign here, that means they're exactly same. And if this sign is not there, that means it is a proper subset, that this will go properly into this. So this is how to remember these symbols. So note, if a set has only one element, we call it a singleton set. So this is a set has only single element, is called a singleton set. And if this element is not there, then it is an empty set. So now here I write the set of irrational number in a set builder form. How do you write? Here T equal to X such that X belong to R and X do not belong to rational number, because you want set of all irrational number, and this irrational number belongs to R and also rational number also belongs to R. But I want only those R which belongs to irrational number, that is X which does not belong to rational number. So the set of all irrational number means these are all irrational number. To understand all this better, please refer my class 9 and 10 lecture on numbers. Now intervals as subset of R means this real number. You have infinite number of real numbers and you can have a set where this extreme point may be included. In this case, this dark spot means it is included and I represent as a square bracket, and if it is not added, included in the set, I keep it this parenthesis, this open circle. So here 2 open circle means 2 parentheses, here 2 square bracket, here 1 square bracket. This side, this point belongs to this set but point B does not belong to this set. Here point A do not belong to the set, is open, and that point B belongs. So how do you write in a set builder form that this set A comma B is equal to X such that A is less than X, this number is less than X but not equal, so it's not included in this, but X is less than B and equal to also, so this point is also included in this set. So similarly, just pause and go through these three also. Now power set of A. In introduction, in the first slide, we have briefly mentioned what do you mean by power set of A. As I had mentioned there, that it is the collection of all subsets of a set A is called the power set of A. It is denoted by P of A, and in P of A, every element is a set. So what do you mean by that every element is a set? Suppose you have set A containing these two elements. This element 1 is a subset of A, or set containing only this element 2, okay, here is again a subset of A. So all these are subsets. So all these elements are subset of A. Null set is a subset of all sets. So I have to introduce this, then 1, then 2, and then combination of 1 and 2, as I had mentioned in the introduction. So you have there 4 elements. So number of element in power set of A is 4, and this 4 is nothing but 2 to the power 2. So this 2 is the number of element. We will see it and we'll prove also. Now suppose if I add one more element 3 to this, then I can write this 1, 2, then 1, comma 2, and put 3 also to each of them, 1, comma 3, then 2, comma 3, and 1, comma 2, comma 3 also. So now you will have 4 extra term containing element 3. This 1, then 2, 3, and 4. So earlier it was 4. Again now you have 4 plus 4, 8. So 8 is 2 to the power 3. So if you have 3 element in any set, then the power set of A will be 2 to the power 3. And if the number of elements in A is m, that is number of element in A is m, then it can be shown that number of element in power set of A will be 2 to the power m, this m. And this m is nothing but number of set in power set of A. So how do you prove this? We can prove by induction, which we have discussed elaborately in class 10. So I will again request student to go through my class 10 lecture to understand it much better. So what is proof by induction, or it is called an induction method. So in induction method, step number 1 is you have to show that for n equal to 1, it is true. That is, if you have only one element, that A has only one element A1, then you have here two element. One is the empty subset and this A1, this element. You cannot have any more combination. So power set of A is 2, and 2 is nothing but 2 to the power 1. So it is true for 1, for n equal to 1. So here this 1 is this m, which is the number of element in set A. That is 1. Now step 2 is you assume that P of n is also true. So if you assume that if P of n is true, then you show that if you replace n with n plus 1, you get the required answer. So here we will show this. So here I say that if a set have n elements and has 2 to the power n subset, then a set that has n plus 1 element will have, instead of n here, 2 n plus 1 subset. So this we have to prove it. So how do we prove this? Very simple. Here let x is equal to this n number of elements, a1 comma a2 up to an, and cardinality means number of element in this is n, and we are assuming that it is 2 to the power n subset for the set x. So here we first assume this one. So now I put another element, n plus 1 element, that is a subscript n plus 1. So one more element I have added it. So now cardinality means number of element here is n plus 1. So what is the power set of x? That is 2 to the power n, and if I add one more element, as I had mentioned here, when I added one more element 3 to this, so it will go through all the element, and again you will have 2 to the power n. So for n element you have 2 to the power n, and for if I add this also you get another 2 to the power n. Here as I have shown here 8, that is 4 plus 4. Okay, 4 for only 1 2, then it becomes 8 if I add one more element. So that is I have written it twice of 2 to the power 2, that is 2 to the power 3. That is the power, this 2 plus 1 here, this power is 1. So 2 plus 1 is 3, so 2 to the power 3. So here the power set will contain this 2 to the power n subsets with the combination of this, and when I add this one I will have another 2 to the power n. So twice 2 into 2 to the power n will be 2 to the power n plus 1. So this is true for n plus 1. I am skipping many steps. Please fill the gaps so that you will understand more better. So therefore a set y has 2 to the power n subset without a n plus 1, as I said, without a n plus 1, only this one, and then another 2n subsets with element a n plus 1, as I have explained for this case. Just pause and go through it if it is still confusing. So in total y will have twice into 2 to the power n, that is 2 to the power n plus 1. So this is proved by induction, that if it is true for n equal to 1, and if you assume that it is true for n equal to n, then the form what you get here, this is the same form, only thing you substitute n to n plus 1. So here now I introduce another concept called universal set. So an universal set is a set that contains all the elements or objects of other sets, including its elements. So I call this thing as a universal set. It contains all the elements in set A, and it has its own elements also. And this universal set is typically denoted by capital letter U. Here I'll give an example. U as a collection of all living thing on planet Earth. So in this case, this is a universal set, all living thing, and the subset is, in this case, the set of all mammal is a subset of this U, set of all the reptiles and set of all all the birds becomes a subset of U. Now let me introduce another concept, that is complement of a set. Universal set, it contains its element plus elements in A. Now suppose if I remove all the elements from A, then whatever is remaining is U minus A, and this is your A prime. This is a complement of A. So no element in A prime belongs to A. So I can write A prime is equal to this U minus A. So here I am writing it. Let U be the universal set and A be a subset of U, as I said here. Then the complement of A is the set of all elements of U which are not the element of A, as I had mentioned earlier. Symbolically we write A prime. Here I am writing apostrophe for my easiness, but consider this apostrophe as prime throughout this lecture. So symbolically we write A prime to denote the complement of A with respect to U. And I can write this in a set builder form. A prime is equal to X such that X belong to U but does not belong to A, okay, and does not belong to A. Obviously that means A prime is equal to U minus. We note that the complement of set A can be looked upon alternatively as the difference between the universal set and the set A. That's what I have shown it here. So as I mentioned that sometimes this A prime can also be written as A superscript C. This is a complement, or you can write as A bar. On top of A you put a bar. Now we will introduce a very important concept in set theory which is called as De Morgan's law. So here first I will talk about De Morgan's law of union, and similarly there is a De Morgan's law of intersection which I will show it here. So here it states that A union B, the complement of it is nothing but A complement intersection B complement. So here you see A union B is this circle. So this would have been shaded blue here, but I am taking a complement. So complement is going outside. So this is not been considered now. So this is your A union B complement is outside, which I have written it here, this blue region. And this is equal to A prime, that A complement intersection B complement. So here you can see very easily A complement is this blue region and B complement is this blue region. Now if I intersect, these are the only common things are remaining. Again here this will become white, and this again then they are not common, so they will become white. So you have this figure. So you can see that complement of A union B, that is equal to complement A prime intersection complement B. So as I said, similarly the Morgan's law of intersection, that is if A intersection B, the complement if you take it. So this is A intersection B. The complement means this will become 0 here, and rest of the thing will become blue. So this region is A intersection B complement of it, or you say complement of A intersection B. Okay, this is all blue region. So how do you show this? Again, it is similarly use this diagram to show this. So this is obvious. This A intersection B complement is this blue region. Now how you show this one? This is A complement union B complement. That is this blue region is A prime and this whole blue region is B prime. So I simply add here, it is not and, it is or. So it is or means if it is here or here it is true. So now I will have this Venn diagram where this also will become blue, this will also become blue. Just pause it, think what I am saying. It is not very difficult to understand. We can prove this by argument also without using Venn diagram, but I always prefer Venn diagram. But in questions, if they ask you to prove by argument, you have to do by argument. So if they ask you to show by Venn diagram, then you have to do by Venn diagram. If they don't ask anything, then you can use either of it, whichever is convenient to you. So now we will prove this one, the Morgan's law of union, that is A union B prime is equal to A prime intersection B prime, which I have written here. So I say that, okay, let X be an arbitrary element in this set A union B prime. Then X belong to this complement of A union B. So if X belongs to complement A union B, but will not belong to A union B, that's what I have written. So when I say union means it either belongs to A or B, I have written here. So it implies that X belong to, now this does not belong to, I am writing it as belong to, okay now. So if it does not belong to A means it has to belong to A prime, and if it does not belong to B means it will belong to B prime. So it will belong to A prime and B prime. So I can write this as X belongs to A prime intersection because it's and here. So this implies this A union B prime is a subset of A prime intersection B prime, which we have shown here. Okay, from here if this belongs to this and this belongs to this, then this A union B prime will be a subset of this A prime intersection B prime. This is what I have written. But now you have to show the other way around also, that again let Y be an arbitrary element Y belong to now this A prime intersection B prime, then Y will belong to A prime and B prime because it's intersection, so it is and. So because of this now Y will not belong to A or B. So now this or is nothing but union. So I write Y does not belong to A union B. So if it does not belong to A union B means it will belong to A union B prime. So Y belongs to A union B prime. So this implies that this Y belong to A prime intersection union B prime is a subset of A union B prime. Just pause it, go through it. It's not very difficult. So from 1 and 2 we see that A union B prime, that is complement of A union B, and A prime intersection B prime, that is complement A prime intersection complement of B, are subset of each other. Since they are subset of each other, hence they are equal to each other, as we had seen it earlier in our previous slides. So similarly you can prove the De Morgan's law of intersection here. I will not go step by step, just pause it, go through it, and I'm sure you will be able to understand. It's the same, exactly same thing, just slightly I have rearranged the symbols. So again you can show here that A intersection B prime is a subset of A prime intersection B prime, and then again this is a subset of this. Here I have shown this is a subset of this. We have to show both, that this is a subset of this is a subset of this. So if both are subset of each other, they has to be same, which we have seen it earlier. So that's what I have done here. So A intersection B prime is equal to A prime union B. Just pause and go through it. Now we will talk about difference of two sets, that is set A and set B. So here the symbol is A difference B, that you can show it as this is A union B minus this intersection region. So this is the difference between this A and B. These are the common, and this shaded region, this orange and green, are the difference of set A and set B. This we had discussed this in introduction slide 1 briefly, but here let me repeat it. That is A difference B is a set of all those elements which belongs to either to set A or to set B. This is intersection region, does not belong to this, either to this or to this, but not both. That means not both. This A intersection. So A delta B is also expressed that as I have written here, A union B minus, you have to chop this off. So now you have this shaded region as a difference between A and B. So A minus B, as I had said earlier, that is A, this minus B is, this is B prime is complement of B. So if you take the intersection, this and this you have common, so you will have A minus B. Just draw in paper and pen, shade it and see. So this A minus B is nothing but A intersection B prime, because this A and B prime is here. So this will not be included in B. So when you take an intersection of B prime with A, you will not get this region. Just draw with paper and pen and see. So similarly, B minus A is nothing but this is B, and then A prime is your whole region, and if you take an intersection of this complement of A and B, you will get B minus. So here I write B minus A is complement of A intersection B. So A difference B is equal to your A minus B, this region A minus B, union of B minus A, or it also means A intersection B prime, union of A prime intersection B. So it is immaterial whether I write it here or here. So A intersection B is same as B intersection A. So here I show some more Venn diagrams, that is if you have set A, B and C. So when you are adding this, there is A union B union C. Here I can write as A union B union C. So I can take either first B union C and then take a union, or I can take A union B and take a union with C. So it is a sort of associative, and also it is a distributive property also, that is A union B union A union C. Okay, just think about it to draw it, so you will get overlap regions, and this is shaded in blue color. So similarly, A intersection B intersection C, I can write as A intersection B and then intersection C. So again this is an associative also, and at the same time it is distributive also, that is A intersection B intersection A intersection C. So this is the shaded region of intersection. This is a common region. A is here, B is also here, and C is also here. So this common region is A intersection B intersection C. Very trivial, I know. So now we'll go a bit further, that is A union of B intersection C is equal to A union B intersection of A union C. So how do you show that? This is, suppose you have, first I do this in the bracket, B intersection C. So you have this blue region from here to here, and then I take a union. So take a union with A. So I have this total blue and this blue region. So this is what is shown here. So this is same as A union B. If I take A union B, I will have this A and B as blue and not the C. And then I have A union C. So this will remain now white. This will become blue. So now if I take an intersection, I know in this was not common, and in this B was not common. So I get this region. So this shaded region from here is same as the shaded region in here. So one can say that this relation is equal to this one. So similarly, this A intersection of B union C. So first we take this in the parenthesis B union C, that is this whole region B and this whole region C will become blue. So the union will be this whole thing, and but now I take A intersection. So I take this A. So this is intersection means common area. So now this doesn't belong to this area, so it cuts here. So I have this region is shaded in blue as A intersection B union C. Just slowly you also go through it. I'm sure you will able to understand. And similarly here A intersection B is this blue region, and A intersection C, this A intersection is this blue region. So this blue region plus this blue region union is, so again you get the same figure either using this rule or this rule. So now since we are well versed how to manipulate this union and intersection, so the difference of A difference B, which is this, you can show that this is equal to this or vice versa. So here I have shown that use distributive property, that is this A intersection B union A prime intersection B. This same thing I have written here. So I can club this as one entity. So this union A prime, this union A prime, and then this intersection B. So I will not go through whole step. This is all self-explanatory. So kindly go through it, and finally you will get this A difference B is what we have shown here. This is the definition. So this sometime they may ask to prove like this using distributive property and De Morgan's law, but which you can see here and can do it yourself. So here I have used only few concepts, that is A union A prime is nothing but universal set, and also I have used De Morgan's law, that is it is this B prime union A prime is A intersection B prime. Just go through it, it will be simple, and using one, that is A minus B is A intersection B prime. So here I have considered this as A here, and this is B prime is nothing but A minus B, so this is A minus B here. So go through it carefully, write it down, I am sure you will understand it. So I can write this set difference, that is set A difference B, in a set builder form, that is X such that X does not belong to A intersection B. So it does not belong to, this is a white region, so it belongs here but does not belong here. And similarly X such that X belong to A, X belongs to A but does not belong to B, or okay, that means you are taking a union, or X belong to B and X does not belong to A. So this is a set builder form. And so similarly I can write this A is A minus B union A intersection B. Just kindly go through this figure. So here this is A, this is A minus B is this region, and union of A intersection B, this A intersection B is this region. Okay, so this intersection plus this A minus B union of this will give you total A. Okay, it's very simple, it's self-explanatory. Similarly B minus A plus or union of this B minus A set with union of A intersection B, you get B. This is what I have written here. So these are very simple, just draw in paper and pen quickly and you can know this relation. These are all very simple. Now let us discuss number of objects in sets. So if A and B are finite sets, this is here A and set B are finite sets, then prove that number of element in A union B is equal to number of element in A plus number of element in B minus number of element in A intersection B. So this is very obvious. The number of element in A, this region is also included in A, and number of element in B, again this region is also included. So now you are including this twice, so you are counting it twice. So you subtract from number of element in A plus number of element in B minus number of element in A intersection B. That is what we have written. So it is obvious. So how do you prove mathematically? So here I have written, note that the set A minus B, this is A minus B is this light blue region, or so you can write as A intersection B prime, what we had seen it earlier, but let us ignore this for the time being. So you have set A minus B, then set A intersection B, and set B minus A. B minus A is a set in this light blue region. So these are all disjoint. Therefore, number of element in A union B is equal to number of element in A minus B plus number of element in A intersection B, this set, and number of element in B minus A set. So it is very clear from here, this number of element A minus B plus number of element of A intersection B, this is equal to number of element I have written as number of element A. This red one, this two, if I add, I get this one. Similarly, I write number of element B minus A plus number of element in A intersection B. So I have added this one here. So I have to subtract to balance it. So now this blue term is nothing but number of element in B. Okay, number of element in set B minus A plus number of element in A intersection B. The total will give me number of element in B. So I have written number of element in B. And this is this minus number of element in this, which we have subtracted because we have added this. So this proves this equation 1. And also from this expression 1, I can write, if I bring this here, that is number of element in A union B plus number of element in A intersection region B is number of element in A plus number of element in. Sometimes this kind of identities are required, so I have written it here. Now this same thing we can derive in a different manner, so it is up to individual how they derive this kind of identities. So here another simple way. So number of element in this green area I call it A, and number of element in this blue region I call it B, and number of element in this intersection region I call it C. So I can always write that number of element in A is A plus C and number of element in set B is B plus C. So I can write like this. So number of element in A union B is A plus B plus C. The whole thing you add it. So this is nothing but I can take A plus C plus here B plus C. This I have added. So since I have added, I will subtract it here. So now I know that A plus C is nothing but number of element in A plus number of element in B, and C is nothing but number of element in the region A intersection B. So this is also very similar. So whichever you feel handy, you can use it. So there is no unique way to solve these identities. Now second, if I add another set C apart from A and B are finite set, then prove that number of element in A union B union C is number of element in A plus number of element in B plus number of element in C minus number of element in A intersection B minus number of element in B intersection C minus number of element in A intersection C plus number of element in A intersection B intersection C. So this is very similar to this one. So here I have just added this number of element in C, and because I have added C, of course it will intersect with B and also it will intersect with A, and then because of C, this is number of element in A intersection B intersection. So how do you prove this? This is again very simple. We'll prove in this line. So I write number of element in A. See here I have this set A. So number of element in set A is A plus D plus G plus F. So this one. In set B, number of element is B plus D plus G plus E. And similarly in set C, it is C plus E plus G plus F. So this is what I have written here. Number of element in A is A plus D plus F plus G. Just refer to this figure. Similarly for NB, I have written, and similarly for NG. Now if I add this number of element in A plus number of element in B plus number of element in C, I will get A plus B plus C plus D plus E plus F plus G. So I write here. So I know here there are how many D's? There are 2 D's, 2 E's, 2 F and 3 G's. So I have used 1 D, 1 E, 1 F and 1 G. So the remaining one I arranged like this: D plus G, then plus E plus G plus F plus G. And since here we have only 3 G's, I have already used 1 G, 2 G, 3 G. So I add one more G here to make it F plus G, and then since I have added 1 G, I subtract it here. So this is A plus B plus C, D, E, F and G. This is the whole thing is A union B union C. I can write this. And D plus G, this is D plus G. This is A intersection B. So here I have written number of element in A intersection B is D plus G. Similarly, number of element in B intersection C, this is B intersection C is G plus E. So here I have written G plus E or E plus G, and then number of element in A intersection C is G plus F. So I have written here G plus F, and this is minus G. So therefore I can write this A union B union C. I take all these steps to the left hand side, and I can get number of element in A union B union C as A plus B plus C, number of element in this minus number of, all this will go in the left hand side, will become minus, and this minus will become plus. So here this is plus. So similarly you can extend this to many sets, and then this thing becomes more complicated. So maybe in next chapter or in higher class we will show you how to generalize this same thing with many more sets in a short form. Here I would like to point out this number of element in A is related to the probability, that is what is the probability. Suppose you have, this is your sample space, and for any event to occur, what is the probability? So probability of event occurring in this is always 1, because this is the whole sample space. So any event can happen. Suppose there are some elements here, all these elements possible to get it. So probability is always 1. So as we discussed in the previous slide, what is the number of element of A union B if they are disjoint and there are no intersection? So I simply write number of element in A plus number of element, and suppose it is intersecting, then I write minus the number of element in A intersection B. So this number I can directly write in terms of probability, and we will see in the section probabilities when we discuss, that is probability of any event occurring in this region A union B is probability of event occurring in A plus probability of event occurring in B, and these two, since they are disjoint, these two when you add you will get 1. So similarly, what is the probability of getting A is 1 minus probability of not getting A, and similarly probability of B is 1 minus probability of not getting B, and this you can see very clearly from this statement. So similarly for this also you just substitute n with probability, that is number of element with probability. Similarly for if you have 3 sets, this we have proved it. So similarly you substitute number of element with P and same relation holds. So we will discuss this more, as I said, in the section probability chapter. Okay, now let us discuss one example based on a number of element in a set. So here a college awarded 38 medals in football, 15 medals in basketball, and 20 medals in cricket. If these medals went to a total of 58 men, so 58 people have got it. Of course some may have got 1 medal in football, 1 medal in cricket, 2 medals they have got, some might have got 3 also. So total 58 people have got it, and these are the number of medals, and this is the total number of men who have got it, and only 3 men got medals in all the 3 sports. So in all the 3 sports only 3 men have got it. How many received medal in exactly 2 of the 3 sports? So what is the intersection between got 2 medals? So how do you find it? So here I describe the set. This is for football, this is for cricket, and this is for basketball. And here B is number of men who have got medals for cricket and football. This A is number of men got medal in football and basketball, and C is number of men got medals in cricket and basketball, and D is number of medals men have got in football, cricket and basketball, all of them, intersection of all. So how do you do it? So I write number of element in this football union basketball union cricket, F union B union C, I will label as this capital letters, alphabets, and that is equal to number of element in F plus number of element in B. This is the formula which we have written it here. I am writing it here, except that A becomes F, B is a basketball, and C is a cricket. So now this is given to you. So many men have got it. That is how many? 58 men. Total of 58 men got the medal, out of which 38 got medals in football. Okay, NFF. 15 got in basketball, 20 got in cricket, and in this one 3 of them got. Total 3 men got medal in all the 3 sports. So now I don't know this, and they have asked us to find how many of them got medals in 2 sports. So this is the thing which we have to find. So now I take this in the left hand side and I bring all this number in one side, and I get this number as 18. So number of element in F intersection B, this is F intersection B is A plus D, and similarly number of element in F intersection C, that is F football and cricket, is B plus D. I write B plus D. Similarly number of element in basketball and cricket is D plus C, so I write here C plus D. So this is equal to A plus B plus C plus 3 Ds, and this is equal to 18 from here. So D is been told that 3 men got it, so I substitute D as 3. Okay, 3 into 3 is 9, so this 9 will go here. 18 minus 9 is 9, so A plus B plus C is equal to 9. So 9 men have got medals in 2 sports. Please pause it and refer this figure and try to understand this problem. Now some more identities what we have done in our previous slide, just a revision. So number of element of A union B we have shown it is, this is the equation we have shown it, and if they are disjoint then this intersection is 0. So I simply write number of element of A union B is just number of element in A plus number of element in B, because this is 0, this is a disjoint set. And now from this equation I can get many more identities, just rearranging this. I number of element in A, I take this 2 side, here is number of element A union B, this minus becomes plus here, and this minus of NB is because here it is plus of NB. So similarly from 1 again you can do this also, there's number of element of A intersection B in this term. Just similarly you rearrange it, it is written here from 1. So similarly you can find number of element in B. Now here number of element in universal set, this is U means universal set. So what is universal set? Here I have written number of element in A union B. Suppose this is this orange, blue and green, you add them, number of element there, plus number of element in the complement, that is this pink region here. So that will give you total U, this pink region plus orange, blue and green. So this is what it is. So this is I have written here. So this is number of element element in A plus number of element in B minus number of element in A intersection B, because you have counted it twice. So we have to remove one set of counts from this region plus this whole pink region, and now A union B complement of it. So when you say complement, this region is not included. Okay. So please pause and do and practice this. From here you can understand these things much more easily. Now number of element of complement of A union B is, again I rearrange this from 6 here and I will get this. So similarly from this figure we can find that what is number of element in A union B is nothing but number of element in A minus B plus number of element in B minus A, this green region, plus number of element in this blue region, that is number of element in A intersection B. So these are very trivial, I know, so please kindly go through. So similarly I can write number of element in A minus B as number of element in A union B, this full thing, orange, blue and green, minus this green and blue, that is B. So this I have written minus B. So that will give me the orange region, number of element in the orange region. So similarly number of element in the orange region is number of element in A minus number of element, this blue region you subtracted. So now I think you are becoming expert how to do this kind of a manipulation in using Venn diagram. So similarly number of element in A complement, this is your A, and A complement is this pink region and this green region also, because A complement is outside A, so green is outside A. So number of element in A complement is number of element in this universal set, which is shown in pink, minus the number of element in set A. So as I said, A complement is all the area except the region A. So just see this and try to understand this. So here we would like to show you how in a different book or different mathematician use different notation to write the complement. So this is your De Morgan's law, that is the complement of A union B. I write as complement of A intersection complement of B. So this we have proved it. So here I am just trying to show what are the different notation people use in practice. So either you can write C or you can write full bar, this complement is bar, this is bar, or you can write prime. So we have mostly used this prime. I have used apostrophe, but to save time I have used it, but it should be prime. Or you write above a tilde sign, here there is a tilde sign, okay, like A bar, you can say A tilde, B tilde, or A union B tilde, and also you can write in bracket and tilde here outside like prime, and then you can write this A tilde instead of A prime intersection B tilde, and similarly you can write instead of capital C you can write small c. And this syntax also very few people uses, that is X such that it does not belong to A union B, that is X not in A union B. So this is X not in A intersection X not in B, and here this is for your reference, this you have set A, B and C. So the union of set A union B union C is this whole colored region, and region outside this I can write as a complement of A union B union C. So similar to De Morgan's law, I can write complement of A prime intersection B prime intersection C prime. Now here if you have two sets, set A and set B, which are disjoint, so if A B is this null set phi, then prove that A minus B bar intersection A is equal to phi. So B bar, this gray region intersection A will be A, we know, because this is the common. When you say intersection means it should be and. This is the common region embedded in U. So I write A minus this B bar intersection A, which is A. So A minus A is phi. Now if A intersection B is not disjoint but it is overlapping as shown here, then I can write this A minus this B bar intersection A. This is B bar will be this pink region along with this orange also. So B bar intersection A will be A minus B, which we have shown here. So this is A minus B equal to B. This we have shown many times in previous slide also. So remember this A minus B is A intersection B bar, or you write it as A intersection B prime. Okay, now quick revision what we have done so far. This is the last slide I think. So here the set of operation. So we know it is A union B is B union A, or A intersection B is B intersection A, and this is called commutative law. You have associative law also, that is A union of B union C is, I can instead of taking union between B and C, I can take between A and B and leave this outside. So this is associative law, and also it obeys the distributive law. All this we have discussed it in detail. Okay, and A union phi, this is a null set. So any set union with a null set is A, and null set intersection A will be null set because there is no common element. So this doesn't have any element. So intersection with this will be phi, and similarly U intersection A, this is a universal set, will give rise to A. So this all we have discussed. This is called the law of identity element. Phi is the identity of union. So this is what, like when you say identity of number, any number multiplied by 1 gives you that number. So that 1 is an identity. So here phi is an identity. This phi union with A will give you A. A law of phi and law of U is also given here. Then there is something called idempotent law, that is A union A is always A and A intersection A, because it's the same thing. So if A element in A and element in A, they are common, so there are all of the elements are common, so it will be A only. Then union of universal set union with A will give you, because this is a bigger set, this A is embedded in U, so it will be always U. It's very obvious. And intersection of universal set with A, this A is embedded in U, so this A is only common with you, so it is A. This is law of universal set. Similarly, A union A complement will give you the universal set, and then A intersection A prime, they become a disjoint, because this is the element not in A, this is the element in A, so there is no common element, so it becomes a null set. So this is called the complement law, and this is one of the most important which you have to remember. All these above are very obvious, you don't have to really remember, this is very obvious, but here you have to remember that is the complement of A union B is nothing but A complement intersection B complement. So these are the De Morgan's law for union and De Morgan's law for intersection, that is complement of A intersection B is equal to complement of A union complement of B. Just remember, this union will become intersection when you bring this prime inside, okay, or bar inside. It may be bar, you break the bar into this. So once you break this union will become intersection. This is how you have to remember. So it's vice versa. This intersection will become union. So when you bring this prime inside, or you break the bar to two different complement, A bar union B bar. So just practice it. This is nothing so difficult. This chapter is actually very simple. Then complement of a complement is the same set. You will get back the original. So this is law of double complementation. And similarly, this complement of null set. So that will be everything, all the elements. So this is universal set. And similarly, complement of universal set is a null set. So this is law of empty sets and universals. So you see, this is the most important chart here, which we have proved it. So if you concentrate on the first slide, which we have shown, and this slide, more or less in between it covers. So in between only we have shown some derivation of such things. Now finally, I will show you an example, and these are mostly used in mathematics, and you will see also in your textbook. So this complement, this is A union B complement union C, and the whole complement C, I can write as bar, as I said, this is a bar. And here I would like to show you how to manipulate this kind of complement. So now I use the Morgan's law. So as I said, this union will become intersection. When you break this upper bar into two bar, this will become C bar, and this is A union B bar, the whole bar. So this is using De Morgan's. So for this also again I can use De Morgan's law, that is A bar, and now here two complement of complement, as I said. So B bar, again a bar, will become B, then intersection C bar. Now if I consider set B and set C as same to set A, all are set A, and if I use this condition here, I have substituted B with A and C with A. So now again I use De Morgan's law, this union will become intersection. So A union A prime, so this becomes a universal set, as I have mentioned it here, okay. Now this becomes U bar here, intersection A bar, and this is complement of U bar is phi, I know. So phi intersection A bar, so any phi intersecting with any set will give you a phi. So this is just to show you how you manipulate such kind of a bar. And here again I can write same thing like this. This is U universal set union A. So this I can again break it using the Morgan's law. Again I get similar kind of thing. So here this is just to show how you manipulate these complements. And here I have shown you how you represent this white region as A intersection B prime, or you can, because it's commutative, B prime intersection A, or you can write as A minus B. This is A intersection B, and similarly this one. So I think we have covered your chapter 1 of your 11th standard textbook, and I have not done many exercise or example because I have done this earlier in class 9 and 10 because they are kids, they were small, but now you have become big. So please kindly go through exercise, and with this understanding you should be able to do your exercise very easily. So thank you, and we will see you in next lecture.